Good morning, everyone. Welcome to the GIS Sea Level Rise seminar. We're very glad to have Dr. Jennifer Walker today. She is an assistant research professor in the Department of Earth and Planetary Sciences at Rutgers University, and also a visiting assistant professor in the Department of Environmental Sciences and Geology at Bryn Mawr College. She is broadly interested in sea level, climate, and impacts on coastal communities, and her research focuses on bridging the gap between short-term instrumental records and long-term geological reconstructions to better understand future sea level rise under a changing climate. Prior to her current positions, Dr. Walker was a postdoctoral associate at Rutgers and earned her doctoral degree from the Department of Marine and Coastal Sciences, also at Rutgers University, studying late Holocene relative sea level in New Jersey. She earned her bachelor's degree in Earth and Ocean Sciences from Duke University, and today she will be speaking on the topic Common Era Sea Level Budgets and the Timing of Modern Rates of Sea Level Rise. So, welcome, Jennifer.
Great, thank you. So yeah, I'm going to be talking about some of my work from the past couple of years about sea level budgets and this time of emergence of modern rates of sea level rise. So we can, start by looking at, we can think about global sea level change during the satellite altimeter era, 1993 to present, and we have about, 10 centimeters of change. But what a lot of my work focuses on is thinking about these longer timescales and putting into perspective what we're seeing in the modern day today. So for example, this is from work from Bob Kopp from his 2016 paper in PNAS, showing that global sea level rise in the 20th century was the fastest that it's been in 2,000 years. So it's important to have these longer timescales, of course, to put into context what we're seeing in the present. And then when we think about, moving forward and climate mitigation and adaptation, we want to be thinking about different spatial scales, of course, as well. So a region that I'll be focusing on today along the US Atlantic coast, and especially in the Mid-Atlantic region and New Jersey, then you have to think about how that compares, of course, to the global average sea level change. So for example, in New Jersey and the Mid-Atlantic, sea level is rising faster than that global average. So here we're looking at about the last 100 years, where we have the benefit of tide gauge records in this region as well, to compare to this global average sea level change. So this is work that was put together for the 2019 report of the New Jersey Science and Technical Advisory Panel, which I was a part of, to specifically look at how sea level has been changing in New Jersey and what we can expect for the future. So we see this faster sea level change in New Jersey and New York City here with the green and the orange compared to the global sea level in black. If we look at the rates of change on the bottom, just from 1993 to 2017, globally then we're looking at about 3.1 millimeters per year of rise compared to New Jersey, which is up at 4.8 millimeters per year. So when you're thinking about these different spatial scales, then you need to be thinking about the different driving processes of sea level change. And one way to do that is to use sea level budget assessments. And these are often focused just on global mean sea level, and they're also often limited to just the 20th and 21st centuries. So here I'm showing an example from Casanova et al. From 2018, where on the left we have our global mean sea level over the satellite altimeter era, and then we have our sea level budget as a table here shown on the right, where we have this breakdown of different driving processes. So this is an important productive way to look at different driving processes But it's also important to think about longer timescales prior to the 20th and 21st centuries, and also look at smaller spatial scales as well, and not only look at global mean sea level. So it's possible to answer these kinds of questions looking at common era sea level over the last 2,000 years, using these common era relative sea level reconstructions that have extended that instrumental record we have from satellites and tide gauges back beyond the 20th century. So Bob Kopp, in that 2016 paper, they produced this global database. So you can see where the data is on the map here of these common era relative sea level reconstructions. And then they were able to produce the global sea level curve over the last 2,000 years, shown in the magnitude in centimeters on the top here in blue. And then we have the rates in 60-year averages in green on the bottom. So using this longer term data then, we're thinking about all of these different driving processes on different spatial scales. Of course, we have our global processes from thermal expansion and ice melt. On a more regional scale, we're thinking about atmosphere-ocean interactions, changes in ocean circulation, glacial isostatic adjustment, tectonics, and then we have those local scale processes as well, such as sediment compaction or anthropogenic groundwater withdrawal, causing additional relative sea level changes. So my goals here for this talk then are first to go through a case study of a relative sea level record that I produced in northern New Jersey a few years ago to explain the types of methods that are used to get these longer sea level reconstructions. I then integrated this new record into an updated global database of both instrumental and proxy sea level records of the common era. And then I'm going to go through two examples of analyses where I used a spatiotemporal statistical model developed by Bob Kopp, one to produce sea level budgets on smaller spatial scales, so they're site-specific common era sea level budgets over the last 2,000 years over the common era. And then the second analysis that I'm going to talk about is this question of the time of emergence of modern elevated rates of rise, or when sea level emerged from background variability. So I'll begin here with this case study. This is a site in Cheesequake State Park. So it's located in northern New Jersey off of Raritan Bay. And on the right here, we have a map of what the park looks like. So it's primarily a salt marsh environment. You have little creeks and tributaries running through it, going into the Raritan Bay, and the Garden State Parkway bisects the middle of the park. So the first step in these kinds of analyses is to go out and study the salt marsh stratigraphy, as well as understand what's happening in the modern environment today. So I use salt marshes to reconstruct sea level in these scenarios. So there's a distinct floral zonation, which is related to the tolerance of frequency and duration of tidal inundation. So as you move from the coastal to the upland area of the marsh, you have your increasing elevation and decreasing tidal inundation frequency. And then the sediment sequences, this is just a little time lapse of taking sediment cores. The sediment sequences act as archives of sea level change as these marshes have built up over the past several thousands of years. So the coring is all done just by hand with these Russian peat corers. Then in the salt marsh environment, I use a multi-proxy approach. So I use foraminifera in particular, as well as geochemistry with stable carbon isotopes, because they exhibit a relationship with tidal elevation. So here are just three examples of these salt marsh foraminifera. So they live in about the top centimeter of salt marsh sediment. They're agglutinated species. And if you go out in the modern environment, and you take samples along a transect from your tidal flat into your upland, shown by the red dots here in the figure on the right, you get these different abundances of species as you move across an elevational transect. So some species you find mostly just in the high marsh environment, some are mostly just in the tidal flat environment. And you get this distinction in the relative abundances of the species through your total assemblage in these marsh environments. I also mentioned stable carbon isotopes. So I use them as a secondary proxy for sea level or elevation because particularly in the mid-Atlantic region, there's a transition from C4 plants to C3 plants that occurs around the mean higher high water mark. So it can just be used as an additional constraint when we're considering elevational changes in a marsh. So I then use a transfer function, which is just a mathematical way to relate our proxy, which is the foraminifera, to our environmental variable, in this case, which is elevation. So it's a foram-based transfer function then. It's been enhanced using a Bayesian approach that employs those foraminifera as well as a secondary proxy of geochemistry. And so this was developed by a colleague in Ireland, Niamh Cahill. So we can go out, right, understand what's happening in the modern environment with these sea level proxies, and use a transfer function and validate that transfer function looking at the predicted versus observed elevations in the modern environment to understand the relationship. So then we can move to the sediment record. So if you look just at an example transect of the stratigraphy at Cheesequake, this is showing a series of cores here where the top several meters are the salt marsh peat, which is what we're looking for to be able to reconstruct sea level. And then at depth, it became kind of more minerogenic, and you end up with this sandy, shelly clay. So I chose the core here, shown by the red circle, because that's where we have a thick sequence of salt marsh peat, where those salt marsh foraminifera will be preserved in those sediment in that sediment core. So then we apply the modern analogs to these fossil counterparts and eventually then estimate paleomarsh elevation for individual samples. So as an example for this core here, these are just four of the most dominant foraminifera species, where you can see their relative abundances with depth. We have our bulk sediment stable carbon isotopes in green, and then we have the transfer function estimates of paleomarsh elevation. So to get relative sea level, you can just subtract the paleomarsh elevation then from your sample elevation from the core. So using these methods then with the foraminifera, this is how we're getting our relative sea level change. And then of course, we just need to add some kind of time constraint to when these changes are occurring. And to do that, I use a variety of different dating techniques within this Bayesian age depth framework. It's a Bcron, which is an R package to produce an age depth model. So here we're looking at just the ages with depth. So for most of the core, I'm using radiocarbon dates of salt marsh plant macrofossils. And then for the upper portion of the core, it's a variety of pollution, chronohorizons. You can use cesium-137 from nuclear bomb testing, and also look at changes in pollen abundances associated with European settlement and deforestation, such as ambrosia pollen is common for the mid-Atlantic region. Then we can take our sea level information, put it together with the chronology, and we have a relative sea level record for this location. So we're looking here at relative sea level in meters over about the last 1,000 years. The boxes here are representing the vertical and chronological uncertainties associated with each data point. We have that spatiotemporal model predictions here with a mean with 1 sigma uncertainty. And then it's important to validate this proxy reconstruction with instrumental data as well. So I have here plotted the Sandy Hook tide gauge sea level data, which is located fairly close to the study site, and you can see that they line up quite well. So now we have a sea level record going back about 1,000 years. We can use that spatiotemporal model then to get more information about the magnitudes and rates of change. So if we look at this over the last 2,000 years now, where we have our sea level on the top and the rates and 60-year averages on the bottom, over the last 1,000 years, sea level has risen by around 1.5 meters in northern New Jersey. And then if we look at the rates of change from 0 to 1700, we're looking about 1.3 millimeters per year. And then we have a higher rate of over 2 millimeters per year from 1700 to present. So this is some of the methods that I have used to reconstruct sea level change over these longer timescales. And this is, of course, just an example from one location. But then you can combine all of these records that are produced around the world to have this database of common era relative sea level reconstructions. So for the analyses that I'm going to show that I have done in the past couple of years, I've updated that global database since 2016 as new data becomes available. So now we have this global map of where we have these high resolution common era reconstructions. So one of the analyses that I did using this database then is to produce these common era sea level budgets. This is work that I had published in Nature Communications in 2021. So it's thinking about using the sea level budget approach, but in a new way to look at longer time scales and look at smaller spatial scales at individual locations. So I used 6 sites along the US Atlantic coast from Connecticut, New York, northern New Jersey, which is the record I just showed you, 2 in southern New Jersey and 1 in North Carolina. And all of these are salt marsh based 4AM proxy reconstructions. So if we look at the spatiotemporal model results here first, just from each of these 6 sites, we can look at relative sea level in meters of the last 2,000 years. So first, of course, you can already see some spatial variability where you're looking at just over 2 meters of rise in Connecticut, and you're looking at between 3 and 3.5 meters at those locations in southern New Jersey. But it's virtually certain that at all of these sites that the 20th century rate of rise was faster than during any preceding century in the Common Era. So earlier I showed, the same statement for global sea level rise, but it's also true at these individual locations as well. So I want to walk through kind of an example of how this Common Era sea level budget approach works, continuing with our example from northern New Jersey. So we're looking here at the rates in millimeters per year over the last 2,000 years. The total rate is shown by the black dotted line. And then we have these 4 components based on different spatial scales. So there's a global component in red, which would be common to all of the sites in the database. There's this linear component in gray, which is constant through time. There's a regional nonlinear component in blue. And then there's this local component in purple, which is unique to each individual location. So what you can do with this then is basically you have a budget using these 4 components in 100-year time steps over this 2,000 years. So if we look at the first 100-year interval from 0 to 100, we have this total rate of around 1.4 millimeters per year. And most of that is due to that linear component, which is making up 92% of the budget at that time period. We look at the most recent 100 years, 1900 to 2000. Now we see this redistribution in those budget components where the global component due to modern climate change is almost equal to that linear component. And we have a much higher rate of greater than 3 millimeters per year. So I want to break down kind of each component here, beginning with the global. So this is looking at the global sea level curve over the Common Era. So I showed the original from Capital 2016. That was then updated by Capital 2018, and then the study updated again in red. So through each of these analyses, more data was added to that database, and we see kind of similar overall trends, but maybe a smoothing of some of that variability through time. And overall, that global component is really relatively small until you get the onset of modern rates of rise. So that by 1950, global sea level change is responsible for about 1/3 to 1/2 of relative sea level change at each of these sites that I analyzed. It's very clear if you look here at all 6 of the budgets together that the dominant processes driving relative sea level change are that linear component. So this is a regional scale, temporally linear component of the budget, and it's very consistent with the effects of glacial isostatic adjustment. So if we look from north to south, the rates from Connecticut down to North Carolina, this makes sense based on the former Laurentide ice sheet taking up much of North America. And then these locations were located on that peripheral forebulge just south of the ice sheet. So that region is still subsiding today, and we have yet to reach an equilibrium. So we have this strong linear component due to GIA. Then there's the regional scale nonlinear contribution, which is pretty similar across the 6 sites, which makes sense because they are geographically close to one another. So that's the blue here. And, it's difficult to attribute changes to specific processes that are occurring, but you can start to make some hypotheses. For example, this negative regional nonlinear component early in the record, for example, might be associated with long-term cooling within the North Atlantic. And there's also here this, we have this consistent negative regional nonlinear trend that becomes positive beginning around 1600, which may be related to the transition from the medieval climate anomaly to the Little Ice Age, and then broader associated climatic effects within the North Atlantic. So I'm just showing here the budget, just the global and regional nonlinear components of the budget, just so it's easier to see. And we can kind of directly plot those with other climatic proxies, right? So we have global temperature anomaly and global sea surface temperature anomalies on the bottom. And this, of course, clearly shows the increasing global temperatures with our increasing global sea level change in the past several hundred years. If we compare it to changes in ice volumes, on the blue dashed line is showing the rate of Greenland ice mass change. And then we have the 3 other colored solid lines, which are the number of glacial advances. So for example, where we have around 1700 here, where we have this negative global rate, could be associated with this higher number of glacial advances over the same time period, for example. And then we can look at more regional changes. These are proxies for the Atlantic meridional overturning circulation, and then also proxies for the North Atlantic oscillation. So over a similar time period where we see a weakening AMOC, we also have a positive regional nonlinear rate in northern New Jersey and at other sites in the mid-Atlantic. And there's also seems to be this transition of the NAO beginning around 1400 from a longer positive phase to more consistent negative phases after that time period. The local scale contribution in purple, it's both spatially and temporally variable. So for example, in northern New Jersey, this local component was quite small, In other sites like in North Carolina, it was much larger. So the local scale processes that we would consider here are processes like sediment compaction. In more recent time periods, you could think about groundwater withdrawal, and also thinking about tidal range changes, because we are using a proxy that's linked to tidal elevation. So you could have some local processes affecting the record in that way. So you can create these kind of individual budget tables then for every 100 years, where you have your 4 components here: global, linear, regional, non-linear, and local, and the likely processes that are contributing to each of these. So from 0 to 100, we have this rate of around 1.4 millimeters per year because of the dominant linear component. If we move to 900 to 1,000, still, we have this strong linear component, and then we see our big changes occurring from 1900 to 2000 due to ocean density changes and land ice mass changes, which increases our global component. So if we can show that in another way using these charts, basically just to show the redistribution of these budget components over the last 2,000 years. And then this global component is really standing out in the last century. So from this work, and this is also work I'm expanding to looking at sea level budgets from all of North America. So this is just an example from Newfoundland and Florida. So because I was only looking at 6 sites, as I kind of expand this analysis to more locations, hopefully can start to kind of parse out the different processes that could be controlling these different changes, as we're including more data in the analysis. But from this budget work, this is just showing another version of a budget with total rates over time. This led to the question for the next analysis that I want to talk about, which is the timing of the onset of modern rates of sea level rise. So of course, we see our clear increase here happening in the last 200 years or so. So the question I was trying to answer with this is, when did modern sea level rise emerge from background variability? So if we take one of our plots here, our rates and 60-year averages, I divided that into a pre-industrial common era from 0 to 1700, and then the more recent 300 years. And in the analysis then, I was looking at the probability that the average rate of relative sea level for a 60-year interval and all subsequent 60-year intervals in that most recent 300 years were greater than a random 60-year interval during the pre-industrial common era from 0 to 1700. And I defined the time of emergence as when this probability reaches 0.9. This is work I had published last year. So I'll show one example here from northern New Jersey first. So on the left, we have the common era rates, and on the right, we have the rates of the last 300 years, and then the probability that I just described. So in northern New Jersey, I found the time of emergence of these modern rates of sea level rise occurred by about 1889. And then I have an uncertainty interval on that using the 66 and 95% probabilities. So we have a range from 1846 to 1906. Globally, we can do the same analysis using our global sea level rate curve. And globally, I found the time of emergence occurred by 1863 with an uncertainty interval from 1825 to 1873. So this is similar in timing to evidence kind of for the earliest ocean warming, as well as more increased glacier mass loss beginning in the middle of the 19th century. Then from this analysis, I wanted to look at the spatial variability of the time of emergence within the North Atlantic. So this is, if you remember from the database map, This is where there's the highest density of reconstructions that are available around the world. And these are also some of the highest resolution reconstructions. So I just focused on the North Atlantic and used all of the sites in green here, which are all salt marsh based sea level reconstructions that I used for this time of emergence analysis. So what I found is that the time of emergence occurred earliest at sites within the Mid-Atlantic region between 1872 and 1894. Then the emergence was a bit later to the northeast and southeast between 1897 and 1919. And then the latest emergence occurred at sites in Canada and Western Europe between 1930 and 1964. So I wasn't really expecting to find any specific spatial pattern with this analysis, but this was kind of intriguing that it was pretty consistent among these kind of broad regions of when this emergence is occurring with modern rates of sea level rise. So to try to get at what could be causing the spatial variability, I'm just going to show an example here first using 3 different sites from New Jersey, which had one of the earliest timings, Florida, which was intermediate, and Scotland, which was later in the 1900s. So this is the total rate for each of these sites over the Common Era. And then similar to the budget approach, I broke down these records into different spatial components. So from these 3 records, I can remove the global component because that's the same for all of the sites. I also took out then the linear rate. So since this is constant through time. So even though there's a lot of spatial variability in that linear rate, of course, it's much higher in places like New Jersey because of ongoing GIA. It obviously can contribute to the time of emergence since it's constant. So what we're left with then is this nonlinear regional and local rate. So I have the 3 sites plotted here with their time of emergence. So New Jersey is 1889, Florida is 1919, Scotland 1962. And we can see that there's variability in this rate through time at all 3 of these sites until about the last 200 years, where there's a clear divergence in this nonlinear regional to local rate, where at sites in the Mid-Atlantic region, like New Jersey, have this regional rate increase in the past several hundred years, maybe even beginning sooner than that. Sites in Florida in the northeastern US either have a muted increase or they remain pretty constant and don't show any increase at all. And then other sites like Scotland and sites in Canada and Western Europe actually show this regional rate decline. So what this means then is that while sea level does emerge at every location in the North Atlantic by the mid-20th century because of the increasing global component, that there are other regional processes causing this spatial variability among these different sites. And we can see this just showing all of the sites that I analyzed. So starting with the blue to purple in New York, North Carolina, New Jersey, and then moving to the sites in yellow, like Scotland and Greenland. So they're ordered in earliest time of emergence to latest. At all of the sites with the earliest emergence, then we're seeing this regional and local rate increase, driving the earlier emergence. Those northeastern and southeastern sites, that increase is either muted or absent. And then we have this regional rate decline at sites in Canada and Western Europe. So the likely hypothesis right now is thinking about kind of atmospheric and oceanic circulation changes, specifically to do with AMOC. So I showed this AMOC proxy earlier, where we have a weakening AMOC circulation in the last 200 years or so, which does match up quite well with the regional sea level rise that we're seeing at sites within the mid-Atlantic. So as AMOG and parts of the Gulf Stream are slowing down, it could be contributing to this regional rate increase at some of those locations in the mid-Atlantic. It's unclear, right, if these circulation changes would also be causing some kind of regional rate decline at those sites in Western Europe, for example. At least for the most recent past, that kind of makes sense to have a regional rate decline at some of those sites because of Greenland ice melt in the most recent time period. So just to kind of summarize what I've talked about then, it's really valuable to have these high resolution relative sea level records from these salt marsh indicators to think about sea level on these much longer timescales over the last 2,000 years. I've used a new kind of sea level budget approach to look at budgets on smaller spatial scales and these longer time scales, which clearly show that the linear processes driven by GIA dominate relative sea level change. And then, of course, the most significant change in the budgets is the increasing influence of that global signal. And finally, looking at this time of emergence of modern rates of sea level rise, globally, I found that modern rates emerged by about 1863. And then we have this spatial variability in the time of emergence of the North Atlantic, which seems to be pointing towards these atmospheric oceanic circulation changes. But as more data gets added to these kinds of analyses, then we can refine the driving processes here. So thank you very much, and I'm happy to answer any questions.
Thanks a lot, Jennifer. Does anyone have any questions?
I have a question. I can't seem to find the hand. Sorry.
Okay, sure.
Can I was wondering for the historic sea levels in places like, I know you didn't have that many spots in Europe, but have you tried to compare your reconstructions with historical maps or reconstructions?
With like other tide gauge records or?
Well, yeah, I was just wondering, like in Europe where there's good written records, like have you integrated those into your analyses?
Yeah, so in the database that I use with the spatiotemporal model, it includes all of the proxy records as well as all available instrumental data. So it pulls in all tide gauge data, it pulls in the, Europe has some of the longest tide gauge records, so that is all pulled into the model and factored in, yeah.
We have a question from Jeff, I think.
Hi, yes. By the AMOC change, I presume you're meaning that the gyre can weaken in the North Atlantic, and that will spread the water out rather than concentrated in the middle, and that's the sort of gyre component of the AMOC weakening. Is that what you mean? So you're actually getting a slumping of the North Atlantic towards the coastal regions?
Yes, exactly. And specifically with the Gulf Stream, with that part of the circulation, as it slows down, then you're getting water piling up kind of along the coastline. So there have been different analyses, especially just in the past several decades and kind of the last century, of how this process is occurring, where it's exactly causing these changes and the magnitudes. But there is kind of a clear link between those specific circulation changes and sea level. And then I'm trying to relate that kind of on these longer time scales as well.
Stanley, have you looked at the longer time tide gauge records in the UK? Because some of them go back to 1700 or so.
I have any that are available get incorporated into the model. Yeah.
But the Edinburgh one is isostatic rebound, isn't it, mostly?
Yeah.
Any other questions? So I was wondering about the like the gravitational effects, if that could somehow impact your variation with latitude.
Yeah, what you'd expect to see, right, like a north-south gradient from like Greenland ice melt in that region. But I don't see that in the data right now. It could be that it's there and it's kind of being overprinted by other processes as well, for sure. But there isn't a clear kind of north to south latitudinal gradient because of gravitational effects.
And I was also curious about the spatial temporal models that you use to try to reconstruct the sea level. Like what goes into that?
Yeah, that's one that was developed by Bob Kopp. All of the, if you're looking for like the all the equations going into it are kind of available in the papers. But basically you have a series of hyperparameters that are set. So you have different spatial and temporal scales, and that's where I'm getting these different components then for the budgets, because you're setting these scales with the hyperparameters. So you're pulling in a common signal from all of the records, which is your global component. And then you have different, you're pulling out a linear signal from GIA, and then you have your regional and your local parameters.
Do we have any other questions, comments?
I have a question. Nice talk, John. Cool to see all this come together into a single talk. Do you, when you rerun the model, I presume there's some stochasticity. Do you get different times of emergence, or regardless of where you start optimization for the spatiotemporal model, do you always come up with 1863?
Yeah, I did a lot of different tests to kind of validate the 1863 globally and also the spatial variability. So even if you use kind of just pieces of the global database, right? Because it is kind of, what's the word? There is a lot more data in the North Atlantic than other regions of the world. If you take out all the North Atlantic data and run it on everything else, if you just include the North Atlantic, if you change the 60-year average rates to looking at 80 years or 100 years, basically any kinds of changes like that you're making, there's always kind of it's around the 1863, like plus or minus 10, 15 years. So you're always looking at kind of, so with the uncertainty interval that we already put on it, you're kind of always in that range.
Okay, any other questions? Well, I guess we can stop there. So
Okay, thank you.
Thanks very much. Thanks everyone for coming.